Dramatic scene in Texas. In its second test flight, SpaceX's Starship rocket did not stick the landing again.
+1, 2, full duration.
On January the 16th, 2025, the ambitious SpaceX Starship Flight 7, a mission poised to push the boundaries of space exploration, ended in disaster just moments after liftoff. What was expected to be another step toward the future of interplanetary travel turned into a fiery reminder of the unpredictable nature of spaceflight. As millions watched in anticipation, the spacecraft was consumed by a fiery inferno. What went wrong? Could this accident have been prevented? And how will it affect the future of space exploration? Well, SpaceX CEO Elon Musk has revealed why Starship Flight 7 exploded. Let's understand this whole saga from the very beginning. Anticipation for Starship Flight 7. Anticipation for Starship Flight 7 had been building for months as SpaceX prepared for its much-anticipated first launch of 2025, showcasing the V2 variant of Starship. This flight was more than just a test. It embodied a series of crucial upgrades and new mission objectives aimed at overcoming challenges faced during previous attempts. The V2 model introduced a host of enhancements, including better thermal protection, refined aerodynamics, and a more powerful propulsion system, all designed to improve both performance and reliability for deep space missions. It was history in the making, unfortunately, for all the wrong reasons. At Starbase, SpaceX executed the final pre-launch activities with meticulous attention to detail. Fueling and engine chill procedures were carried out precisely to ensure all systems were ready for the high-energy demands of liftoff. The mission would require a record-setting full fuel load of 4.9 metric tons, or approximately 10.8 million pounds of propellant, a critical factor in achieving the required thrust and sustaining engine performance during ascent. Flight 7's heightened anticipation stemmed from the history of delays and setbacks that had marked previous test flights. Each delay fueled the public and industry's growing expectations, making this launch a pivotal moment in proving the upgraded Starship's capabilities. The V2 improvements were expected not only to boost performance during atmospheric ascent, but also to pave the way for future missions that could make space travel routine and cost-effective. This was an opportunity for SpaceX to show that the lessons learned from past challenges had been applied, pushing the boundaries of space exploration. It did not go as planned, but the hopes were high for a reason. SpaceX had long been a poster boy for the spacefaring business, and for good reason. The many successes of Starship. The Starship program, envisioned by Elon Musk and SpaceX in the mid-2010s, was rooted in a grand ambition to revolutionize space travel with a fully reusable spacecraft capable of transporting humans and cargo to destinations as distant as Mars. Musk's vision, laid out in 2016, was clear. Starship would be the cornerstone of humanity's future in space, a vehicle capable of making space travel as routine and affordable as air travel. The path to Starship's current iteration began with the Starhopper, a prototype that was designed to test the key principles of Starship's reusability and rapid development cycle. The Starhopper was a vertical takeoff, vertical landing, or VTVL rocket that featured a single Raptor engine. The initial tests took place in 2019 at SpaceX's testing facility near Boca Chica, Texas, a location that would become the heart of Starship development, known as Starbase. During these initial assessments, Starhopper encountered some technical difficulties, including engine issues and an unexpected explosion, but they were critical to understanding the complex dynamics of controlled landing and the vehicle's potential for rapid reuse. The Starhopper tests, which began with low-altitude hops, demonstrated the feasibility of controlled landings, marking a fundamental milestone for SpaceX. Despite some early setbacks, these tests were pivotal in proving that a reusable spacecraft could return safely to Earth. Building on the Starhopper's lessons, SpaceX continued its development with the first Starship prototypes, dubbed Starship Mk1 and Mk2. These vehicles, intended to test higher altitudes and more advanced maneuvers, were far more ambitious. The first high-altitude test flight took place in late 2019 with the Starship Mk1, but the test ended in an explosion on the ground. Rather than seeing it as a setback, Musk and his team focused on the lessons learned and moved forward with Starship Mk3, eventually refining it into the more advanced Starship Mk4. In 2020, SpaceX achieved a significant milestone with the Starship SN4 prototype, which performed a successful static fire test. This test fired all 3 Raptor engines and validated many of the systems needed for a high-altitude flight. Following this success, SpaceX moved forward with more ambitious prototypes that would soar to higher altitudes and showcase their maneuvering capabilities. By late 2020, SpaceX had ramped up its efforts to test Starship's capability to reach higher altitudes. The Starship SN8 test flight on December 9, 2020, was a pivotal moment in the program's development. The vehicle reached an altitude of around 12.5 kilometers or 41,000 feet, performing a controlled descent and attempting a belly flop maneuver, which was a precursor to the vehicle's re-entry process. While SN8 failed to land successfully due to a methane leak, the mission provided crucial insights into the aerodynamics of the vehicle, which had not been fully understood up until that point. These tests marked the beginning of Starship's evolution from a conceptual vehicle to a functioning spacecraft capable of complex maneuvers. In early 2021, the Starship SN9 test flight followed, also achieving impressive altitudes. However, this flight also encountered issues with its engines during descent, resulting in a hard landing. Despite the setbacks, SpaceX continued to improve and refine the system, acknowledging that each failure was an opportunity to gain data that would push the program forward. A key part of Starship's design was the development of the Super Heavy booster, which would provide the necessary thrust to launch Starship into orbit. SpaceX's earlier experience with Falcon 9 and Falcon Heavy boosters had provided a foundation for developing this new, larger booster. The Super Heavy booster was designed to carry Starship on its journey into space and would also be reusable, similar to the Falcon 9 boosters. Initial tests of the Super Heavy booster began in 2021 and 2022, with a series of static fire tests to demonstrate the performance of its 33 Raptor engines. While the booster's development progressed, SpaceX also worked on refining its recovery methods, such as the development of the Mechazilla arm, named after the mech-style recovery system designed to catch the booster after launch. By mid-2023, SpaceX's Starship program had matured significantly, with numerous test flights advancing the vehicle's capabilities. Starship V2, the upgraded version that was slated for Flight 7, incorporated key lessons from the earlier prototypes. Improvements included better heat shielding, more efficient engines, and refinements to the aerodynamic structure to enhance both ascent and re-entry performance. These advancements were essential to preparing Starship for the challenges of deep space missions, particularly the goal of Mars colonization. The progress made by this point transformed Starship from an ambitious prototype to a vehicle with a much clearer pathway to operational missions. It all seemed perfect at the beginning. Initial testing. Before a rocket like Starship is launched, it goes through many tests to make sure everything works perfectly. One important part of this testing is called cryogenic testing, which involves chilling parts of the rocket with extremely cold temperatures, similar to the conditions the rocket will face when it's filled with super cold propellants, like liquid methane and liquid oxygen. For Flight 7, Ship 33, a version of Starship known as Block 2, underwent this cryogenic testing in October 2024. Its booster counterpart, Booster 14, was also put through similar tests at the same time. This step is crucial because it helps engineers check that all the materials and systems will hold up under the intense cold of space and cryogenic fuels. Booster 14 was then moved out to a special location called OLP-1, which is a launch pad area designed for final testing. Here, Booster 14 did a spin prime test. A spin prime test involves spinning the rocket's engines to make sure that the fuel flows properly and that the engines are ready to fire. This is like doing a dry run, where you don't actually launch, but you simulate the engine startup process to catch any potential issues. Shortly after this, Booster 14 completed a static fire test. In a static fire, the engines are ignited while the rocket is held firmly in place, so engineers can check the performance of the engines without the rocket actually taking off. After these tests in early December, Booster 14 went back to the production site so that engineers could make any final adjustments and modifications needed before the launch. Ship 33 didn't have an easy ride either. It underwent a combination of spin prime and static fire tests. Like Booster 14, these tests were designed to ensure that Ship 33's engines and systems were working correctly. Testing both the spin prime and static fire on Ship 33 gave engineers confidence that the vehicle would be ready for the high-energy demands of flight. Then, on January the 10th, both Ship 33 and Booster 14 performed what is known as a wet dress rehearsal. A wet dress rehearsal is a full practice run of the launch countdown. During this rehearsal, the rocket is fully fueled, and all the procedures, from fueling to the engine startup, are carried out exactly as they would be on launch day. However, in a wet dress rehearsal, the engines aren't fired for long enough to launch. Instead, the test is stopped after a short burn. This final rehearsal ensures that every system, from the rocket's onboard computers to its ground support systems, is working perfectly under real launch conditions. The tests were all clear. NASA's observations. NASA planned to use a specially equipped Gulfstream 5 aircraft to capture critical images of Starship's re-entry and peak heating. The aircraft's mission was to fly into a specific position so that it could see the spacecraft as it reappeared over the horizon and then capture its splashdown in the eastern Indian Ocean during the early morning hours. To get the clearest images possible, the Gulfstream 5 had to fly with all of its exterior and interior lights turned off, which is similar to taking a photograph in a dark room to avoid unwanted glare. However, this requirement also created significant safety challenges, as flying without lights makes it harder for other aircraft and controllers to see the plane. To address this, NASA had to secure a special waiver from aviation authorities and implement strict safety procedures to ensure that no other aircraft would inadvertently fly into the same space. The urgency of the imaging task led NASA to request an expedited waiver from the Federal Aviation Administration so that practice flights could begin as soon as early December over regions like the Gulf of Mexico and southwest Texas. These practice runs were essential for verifying that the aircraft could safely fly its unique mission profile under low-light conditions. On January the 3rd, the Gulfstream 5 was flown all the way to Perth, Australia, where additional practice flights were conducted in the actual landing zone designated for the mission. This extra step helped ensure that the imaging system was perfectly calibrated and that every safety protocol was in place before the targeted Flight Test 7 on January 16, 2025. Australia's Civil Aviation Safety Authority had already indicated that it would honour the FAA's exemption, allowing both the practice flights and the final imaging flight. But why was NASA so keen on observing the test flight? Well, there's a history lesson for that too. The Space Shuttle program, which had been a symbol of American space exploration for decades, ended in tragic failure. The Challenger disaster in 1986 and the Columbia disaster in 2003 were particularly devastating. The latter claimed the lives of 7 astronauts.
It happened just over 1 minute into flight.
These incidents left the shuttle program with a legacy marked by both triumph and tragedy. In the aftermath, NASA found itself dependent on the Russian Soyuz spacecraft for transporting astronauts to and from the International Space Station, a situation that underscored the limitations of existing American space technology. The dependence on a foreign system, one that came with geopolitical and logistical complications, fueled a growing desire within the United States to restore independent access to space. NASA's solution to this dilemma became clear: a new, revolutionary spacecraft that could not only replace the aging shuttle system, but also take American space exploration to the next level. Enter SpaceX's Starship. With its promise of complete reusability, lower launch costs, and the capacity to carry both large crews and substantial amounts of cargo, Starship seemed like the vehicle that would finally deliver the United States from its reliance on Russian technology. Starship's design, with its fully reusable booster and spacecraft, had the potential to lower costs drastically and make spaceflight more frequent and accessible. The anticipation surrounding Starship's development reached new heights, especially after the successful flight tests of SpaceX's other vehicles, such as Falcon 9. Naturally, NASA wished to be on board in this case as well.
Prop AVI GNC, move to section 10.59.
the launch of Starship Flight 7. In the hours leading up to liftoff, the ground crew at Starbase initiated the water deluge system, a critical step designed to protect the launch pad by spraying massive quantities of water to dampen the intense acoustic vibrations and thermal energy produced during engine ignition. As the countdown advanced toward the revised liftoff time of 4:37 p.m. Central Time, final pre-launch checks confirmed that every system was green across the board. At the designated moment, all 33 Raptor engines on the Super Heavy booster ignited simultaneously, marking one of the most powerful engine starts ever recorded by SpaceX. The engines produced a combined thrust exceeding 7,000 metric tons, roughly equivalent to 16 million pounds of force, propelling the massive 120-meter-tall rocket upward with an explosive burst of energy. This extraordinary thrust not only lifted Starship Flight 7 off the ground, but also immediately set the stage for the vehicle to overcome the significant gravitational and aerodynamic challenges inherent in such a high-powered launch.
T-minus 8 minutes and 40 seconds until liftoff. Flight controllers on console.
During the initial ascent, Starship Flight 7 rapidly accelerated through the dense lower atmosphere. One of the critical moments in the flight was the passage through Max Q, the point of maximum dynamic pressure where the rocket experiences the highest aerodynamic forces. Successfully passing this phase was made possible only by the rigorous engineering behind the rocket's structural integrity and thermal protection systems. As the rocket continued its climb, onboard telemetry and sensor data confirmed that the vehicle was operating within the expected performance parameters. The precise synchronization of engine burns, combined with advanced guidance systems, ensured that Starship Flight 7 maintained the correct trajectory, setting the stage for subsequent events such as stage separation and eventual orbital insertion. Each phase of the ascent was meticulously monitored by Mission Control, whose continuous stream of data provided real-time validation of the rocket's performance. But then, things went south. Tragedy strikes. The mission profile for Flight Test 7 was designed to mirror elements of the previous successful launch while incorporating additional in-space maneuvers that would showcase Starship's full capabilities. Like its predecessor, the flight was set to target a controlled splashdown in the Indian Ocean. However, this mission was expected to push further into the realm of orbital operations. Had the vehicle achieved its intended trans-atmospheric Earth orbit, a trajectory that takes the spacecraft beyond the upper atmosphere into a stable orbit around Earth, it would have initiated a series of complex in-space operations that would mark a significant milestone in the test program. One of the key in-space maneuvers was the planned engine relight. This involves reigniting the Starship's engines after the initial boost phase, a critical demonstration of the vehicle's ability to restart its propulsion system while in orbit. Successfully performing an engine relight is essential for missions that require adjustments to the orbital trajectory, rendezvous with other spacecraft, or deorbit burns to ensure a controlled re-entry. The relight maneuver would have proven that Starship's engines are not only powerful at launch,
blow up an engine because you've got a high production rate, you've got a bunch of engines coming after that.
but also capable of sustaining operations in the vacuum of space, where the conditions differ markedly from those at sea level. Flight Test 7 was also set to deploy 10 demiscible Starlink simulators. These simulators were essentially test payloads designed to mimic the mass, shape, and other relevant characteristics of actual Starlink satellites. Their deployment in orbit would have served multiple purposes. First, it would have provided real-world data on the deployment mechanisms and dynamics of multiple objects released into space simultaneously. Second, these simulators were engineered to be demisable, meaning they would naturally disintegrate upon re-entry into Earth's atmosphere. By tracking how these objects re-entered and broke apart over the Indian Ocean, engineers could gather valuable information about heat shielding, breakup dynamics, and debris dispersal, all of which are critical for designing safe deorbit procedures for future missions. At T+2 minutes and 40 seconds into the flight, Ship 33, a Block 2 version of Starship, ignited all 6 of its Raptor engines, marking the start of its ascent burn away from Booster 14. At this point, the two stages of the rocket separated. Booster 14 then executed a dramatic return to the launch site. Using its engines and grid fins, which are wing-like structures that help steer the booster during re-entry, Booster 14 made a precise landing. It was caught by a robotic system known as the chopsticks on OLP-A, a landing pad specially designed for catching returning boosters. This successful recovery of Booster 14 made it the second booster SpaceX had recovered, following the earlier success of Booster 12 on Flight 5. Shortly after separation, during Ship 33's continued ascent, the rocket began a series of engine shutdowns, a chain reaction of failures that would prove critical. At T plus 7 minutes and 39 seconds, one of the center Raptor engines, which are mounted in the middle of the engine cluster, shut down unexpectedly. Just a few minutes later, at T plus 8 minutes and 2 seconds, a second center engine failed. Then, at T plus 8 minutes and 4 seconds, an adjacent outer Raptor vacuum, or RVAC engine, which is optimized for performance in the near vacuum of space, also shut down. The problems didn't stop there. By T plus 8 minutes and 18 seconds, yet another outer RVAC engine went offline, and by T plus 8 minutes and 24 seconds, the last engine capable of changing its direction to steer the rocket from the center had also failed. These cascading engine shutdowns meant that Ship 33 was rapidly losing the thrust and control it needed to maintain its trajectory. Just 27 seconds after the final engine failure, at T plus 8 minutes and 26 seconds, communications with the spacecraft were lost. At this point, Ship 33 had reached an altitude of 146 kilometers, or about 91 miles. The loss of transmissions indicated that something had gone very wrong. Then, around 3 minutes later, tragedy struck as Ship 33 exploded over the Turks and Caicos Islands. The explosions scattered debris over a wide area, with most of the remnants expected to re-enter Earth's atmosphere and fall into the ocean north of Puerto Rico and the British Virgin Islands. Due to safety concerns, the airspace in the region was closed for over an hour to keep other aircraft away from the falling debris. Following the incident, the Federal Aviation Administration, FAA, stepped in and ordered SpaceX to conduct a thorough mishap investigation into the breakup of Ship 33. This investigation was critical not only to determine the exact cause of the failure, but also to ensure that similar problems would not occur in future flights. As a result, the FAA grounded Starship launches until the inquiry was completed, putting the future flights of this promising vehicle on hold until the safety issues could be addressed. So, what had gone wrong? Elon Musk reveals the truth. After the mission, SpaceX CEO Elon Musk provided an early assessment of what went wrong with Ship 33. He explained that preliminary indications pointed to a propellant leak as the likely cause of the failure. Specifically, Musk mentioned that there appeared to be an oxygen and fuel leak in the cavity located just above the ship's engine firewall. The engine firewall is a protective barrier designed to shield the rest of the vehicle from the extreme heat and energy generated by the rocket's engines. In this case, the leak occurred in a critical area where the propellant, which is composed of liquid oxygen and fuel, is stored and managed. Under normal operating conditions, the design includes venting systems that safely release excess pressure. However, the leak in Ship 33 was substantial enough that it overwhelmed these venting capabilities, leading to pressure levels that exceeded what the system was designed to handle. When pressure builds beyond the venting capacity, it can compromise the structural integrity of the spacecraft. This may result in a rapid and uncontrolled disassembly of the vehicle, which is what appears to have happened in this instance. So, is this the end for SpaceX? Well, history once again holds the answer. Past failures in space exploration. Space exploration has always been a frontier full of incredible challenges and risks. Throughout history, several tragic failures have underscored the dangers of launching humans and complex machines into space. One of the earliest and most harrowing incidents was the Apollo 1 disaster in 1967. During a pre-launch test on the launch pad, a cabin fire broke out inside the Apollo command module, claiming the lives of astronauts Gus Grissom, Ed White, and Roger B. Chaffee. The fire, fueled by a pure oxygen environment, spread rapidly in the confined space, and tragically, there was no time to escape. Decades later, the space shuttle era brought its own share of heartbreak. As noted earlier, in 1986, the Challenger disaster resulted in the loss of all 7 crew members. The shuttle broke apart just 73 seconds into its flight after a faulty O-ring, a small yet critical seal in one of the booster rockets, failed due to unusually cold weather at the time of launch. This failure allowed hot gases to escape and damage the fuel tank, leading to the catastrophic breakup of the vehicle. The Challenger explosion was a stark reminder of how even minor engineering oversights or unexpected weather conditions could have fatal consequences in the unforgiving environment of space. Another sobering moment occurred in 2003 with the loss of the Space Shuttle Columbia. As Columbia re-entered Earth's atmosphere at the end of a long-duration mission, a piece of insulating foam detached from the external fuel tank during launch and struck the shuttle's left wing. This impact created a hole in the heat shield, which proved to be disastrous during re-entry. As the shuttle encountered intense heat, superheated air entered the damaged wing, leading to structural failure and the disintegration of the spacecraft. All 7 astronauts aboard were lost, and the tragedy highlighted the ongoing need for vigilance in maintaining the integrity of spacecraft during all phases of flight. The Soviet space program was not immune to these dangers either. For example, Soyuz 11 in 1971 suffered a similarly grim fate. The Soyuz 11 crew, consisting of Georgy Dobrovolsky, Viktor Patsayev, and Vladislav Volkov, died during re-entry when a cabin vent valve unexpectedly opened, causing the capsule's atmosphere to depressurize rapidly. Unlike the shuttle disasters, this incident occurred in space. But one thing is common here. All of these tragedies taught engineers, scientists, and astronauts invaluable lessons about the inherent risks of space travel. They spurred rigorous investigations, led to significant redesigns of spacecraft and safety measures, and ultimately pushed the boundaries of what could be achieved in space exploration. While these failures are remembered with sorrow, they also serve as important milestones that have shaped the evolution of modern space technology, making today's missions safer and more resilient. So, is this the end for Starship? The short answer, absolutely not. While the failure of Starship Flight 7 was a significant setback, history has shown time and time again that space exploration is built on persistence, learning from failure, and pushing forward. The loss of Ship 33, while unfortunate, is part of the broader journey of perfecting the world's most ambitious rocket system. Just as past failures, some of which cost lives, did not mark the end of space programs, this latest mishap will be another stepping stone toward making Starship a fully operational vehicle. In the commercial space sector, SpaceX itself has a history of turning failures into progress. The early days of the Falcon 9 program were marked by 3 consecutive failures, nearly bankrupting the company, before the 4th flight succeeded in 2008. Falcon 9 also suffered dramatic explosions in 2015 and 2016, yet SpaceX refined the design and went on to make it the most frequently flown and reliable orbital rocket in the world. Even within the Starship program, setbacks have been a constant but necessary part of the learning curve. Early Starship prototypes, SN1 through SN4, either exploded on the test stand or failed during static fires. It wasn't until SN5 and SN6 that SpaceX finally nailed the low-altitude hop tests. Then SN8, SN9, SN10, and SN11 all ended in spectacular explosions, before SN15 became the first fully successful high-altitude landing. Similarly, the first 2 full-stack Starship flights, IFT-1 and IFT-2, were destroyed before reaching key milestones. However, Flight 3 achieved a nearly complete mission profile, and Flight 4 successfully demonstrated Starship's ability to survive re-entry before losing telemetry near splashdown. If history is any guide, SpaceX will not only recover from Flight 7's failure, but will make major improvements to ensure that future flights are even more successful. While the failure of Ship 33 has raised concerns, it is important to remember that the Starship program has already made unprecedented progress. For starters, on March 2024, Flight 3 became the first Starship mission to nearly complete its full mission profile, demonstrating controlled entry into the atmosphere and confirming that SpaceX was rapidly improving its heat shield technology. Then in June 2024, Flight 4 proved to be a historic success as it became the first Starship to survive re-entry, reaching the planned splashdown point in the Indian Ocean. This marked a crucial milestone improving Starship's long-term viability for crewed missions. Similarly, Booster 12 on Flight 5 and Booster 14 on Flight 7 were both successfully caught by the launch tower's chopsticks. NASA also continues to support Starship's development for the Artemis program, where a specialized version of the vehicle will land astronauts on the Moon for the first time since Apollo 17. Moreover, the latest iterations of Starship feature major improvements, including higher performance Raptor engines and more efficient heat shield tiles, bringing the system closer to full operational capability. Elon Musk has made it clear that Starship remains the backbone of SpaceX's long-term vision. Despite the setback with Flight 7, the company is already looking ahead to the next flight. Booster 15 and Ship 34, which are expected to fly on Flight 8, will incorporate lessons learned from previous missions, including improvements to leak prevention, better thermal protection, and more robust engine redundancy. Beyond simply making Starship work, Musk's ambitions remain as bold as ever. The ultimate goal is still to make humanity a multi-planetary species, with Mars as the primary destination. Starship is designed to transport large numbers of people and cargo to the Red Planet, forming the backbone of a future Martian colony. Additionally, SpaceX envisions Starship replacing the Falcon 9 and Falcon Heavy for all major launches, reducing costs and increasing payload capacity. In the years to come, this disaster will be seen as nothing more than a minor setback. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.